So we are talking about single cycle processors, and last time we went through all of this, but I'm going to just go through real quick one more time. We'll look at the LDR first, LDR, R1, R2, and number 5. So all the data path in the single cycle looks like this. Again, these are the name of registers. Inside of this register file, we have stack of registers R0 through all the way down R15. We just need to call their name and produce the content of those registers to here. So these are the 32 bits. These are only 4 bits. And then for store, it's a little bit different from the load. So for the LDR, we're going to read the content of the main memory and put it back into register. Store, content of register is stored into memory, so there's no feedback to the register here. Other immediate ones, we're going to use this extended unit. And for data processing type and the memory type, they all use with 0 extended, not sign extended, 0 extended. Branch not equal to case, so we're going to use this. And then last time there was some confusion, so I add the value 1111 here, so call the register 15. Whatever we store in here, it's going to bring it here so that we can calculate the target address. That's what we did. Now we'll look at this blue line, the control lines. So it's a black and white for the handout. But you know the path of the data versus these are the control line. Control line typically goes into top of the box. Let's take a look at this control unit in here. In this control unit, we have all of this line and the inputs. As you can see, COND, it was 4-bit. So it was 1110 for all the not condition instructions. And then the right-hand side is controlling all of these boxes in here. So we have condition bits, ALU flags, opcode, function, funct, and then RD. And this side is controlling those boxes sent through the conditional logic first and the data path. And these guys just sent directly to the data path. And the sum of this signal, we're going to make it to 0, and depends on the instructions. Now here's the values for all of this. So for your quiz and exams, I'm going to just ask you to find these values. So it is all depends on which instruction we fit into data path. All these values are different. Notice these x's, we talked about last time. What we call these x's, don't cares. If you put either 0 or 1, that's completely wrong. We fit in the wrong value. These are the don't care for store and load in the func. And then there are 2 bits immediate source for these guys, and this is for 0 extended and sign extended. And then ALU, as we talked about this ALU in chapter 5, depends on ALU control line. We're going to add, subtract, and them or them. And also ALU opcode and the func. Based on that, we're going to take care of these instructions, data processing instructions. Okay, so let's go back to our first example. So you highlight all this path last time. So let's go through top to bottom. PC source, the program counter source. For LDR, PC is just PC plus 4, right? In that case, the value of PC source is going to be 0. When do we have 1? Where you get new PC value? From here. ALU, this is the path coming to here. Which instruction was it? Branch. So we're going to calculate the target address, and we need to fit in here. So instead of taking PC plus 4, we're going to have a branch target address. We're going to go. And then mem to reg. So if you look at this line, it's a memory to register. So when we have a LDR, we have to select 1. Do we have any other instructions we're going to have 1? No, because LDR is the only instruction we discussed. We're going to get the content of memory, put it back to register. So that's how you read it, memory to register. So that's to be 1 only for LDR instructions. That makes sense. LDR is the only instruction we're going to get the content of memory store into register. Mem write. So we're gonna write into memory. What's gonna be? Are we writing something into memory in this instruction? No, it's gonna be 0. When do we have a 1? Exactly, store. Store is the only instruction we're gonna make it to 1. ALU control, what is the value? So you have this handout, data sheet. So we have a 2-bit ALU control. What's gonna be in here? Why is 0, 0? It's adding content of R2 plus number 5 so that we can go into memory address and grab the content, put it back into R1. So that has to be 0, 0. What about ALU source? It's going to be 1. What about immediate source? We have the second page, the last table, and that is what? 0, 1. And then register write, it's going to be what? Are we writing into register? Yeah, we are writing into R1. And this rec source, this is 0, and this one is don't care, so 0x. Okay, that's LDR. ALU control, this one. What do we do in here? We're gonna add these two guys. So the ALU should be doing addition. And when we have a negative value, then ALU should be subtract. Okay, so next one we did is a store. Same thing for PC source, ALU control. We're gonna add. ALU source is gonna be 1. Immediate source is gonna be 0, 1. That's the same thing as LDR. Now, mem to rec. That's a different, don't care. Mem write, we are writing into memory, so it's going to be 1. And then register write, no, we are not writing back to register. And then this register source is going to be 0, 1. This guy is controlled this mux. If I select 0 or 1, if I select 0, then I'm going to get this guy and fit into there. If I select 1, I'm going to read this guy and send it to there. But we don't want to do that. So it's a don't care, because in this store instruction, it ends when we write into memory. Done. There is no feedback. Therefore, these guys, we don't care. The next example we did was the add, right? So in this case, we have add R1, R2, R3. They're pretty much the same. And this immediate source is going to be don't care for because we are not getting any immediate value for this. The last one is a branch BNE. The major difference is this guy. This is again new 1 branch instructions. We're going to have this guy as a 1, and the rest is going to be all make sense. And if you are using this example, these values again. Yeah. Oh, from here to here. Shift left by 2. When we have a branch, in the data processing instructions and memory instructions, it's all 0 extended. And there's no shifting mechanism in here. That is controlled by this blue line, right? It's 1, 0. But in the branch, if we have FA, and when we went through this extended unit, it is a sign extended. You're gonna make it to 32-bit. It is a sign extended. Then we can just add the total number of ones and the fill up the front part. At the same time, we're gonna arithmetic shift left. It doesn't matter arithmetic or logical shift. When you shift to the left, we're gonna fit in 0 anyway, so it doesn't matter. And it's the same thing. But when you shift to the left by 2, we have 1, 0, 1, 0, and 0, 0. So the F, E, 8. Why we shift left by 2? Why we do that? What's the effect of shift left by 2? Multiply by 4. Shift left by 1 is 2, and then since we shift twice, the shift left, so we're going to multiply whatever the number by 4. Why? What are we doing in here? We are looking at the target address, right? Target address for the branch, am I right? Target address is going to get into instruction memory and find the right location of the instruction. We're going to grab it. By adding this guy plus content of this is not enough, because all of this instruction is, how long is this guy? 32-bit. How many bytes? 4 bytes. So the address is increment by 4. So getting into the right instruction, we have to shift left by 2 so that we can get the byte address of that instruction. We're getting into multi-cycle. When you compare single cycle versus multi-cycle, this is the positive. Single cycle, it is a simple. However, the cycle time is limited into longest instruction. When you set up the cycle time, we need to measure how long it takes for LDR instruction, and we have to use that as each cycle. That means just as simple as subtract, add a branch. We don't have to even getting into the memory access. It's going to be probably half cycle, but still we have to keep it as a longest cycle. That's the major drawback. And then separate memories for instruction memory and data memory. And then we need to have 3 adders and ALUs. For the multi-cycle, we're going to have a shorter instruction, take a fewer steps, and we're going to be combining these two, and cycle time is going to be really faster. But one drawback is the sequencing overhead paid many times. So we'll quickly take a look at it. You don't have to copy this down. Let's take a look at it, and I'm going to show you one example, or just combining all these multi-cycle blocks together, and then we're going to move on to pipeline. So here's the clock. It's the same as what we had, but this time we have an instruction memory and data memory. We put them together. And then register file, we're going to put it in the last. And if we put them together, it looks like this. We just look at the multi-cycle. So when you put them all together, multi-cycle data path looks like this. And then we look at the single cycle. Based on this single cycle, we're going to put the pipelining. In the pipelining, in this ARM architecture for our textbook, we have 5 different stages. We're going to call it instruction fetch, instruction decode, execute, access to the memory, and the write back stage. So when we do single cycle, instruction fetch, decode, execute, access memory, write back. So in the second instruction, we do this. So it takes a lot. However, when we do the pipelining, after I fetch instruction, I can feed the next instruction. So while I'm decoding in the first instruction, I feed in the second instruction. And the first instruction is the execution stage, and the second instruction is going to be decode stage, and then third instruction is getting into the pipelining. So that way we can have at most 5 instructions at the same time. So here's the diagram real quick. So we have a LDL, add, subtract, and store, or we fit in the pipelining. Then we have IF, ID, EX, MEM, write back. Those are the 5 stages for LDR. And when the LDR is in the instruction decode stage, we fit in add instruction, and then subtract instruction and instruction. So 1, 2, 3, 4, 5. So this guy, that's the maximum number of stages we can do in a single pipelining data path. Okay, 5. So there is, we can calculate as a speed up. So this is what we saw, the single cycle data path. And then we're going to have register. These are the register. These blocks, we're going to have a 32-bit registers. It's not part of this register file, just kind of the storage space. So while we're going from one stage to another, we need to store here. And then when you move on to next stage, we need to read from there, while the second instruction going in here and writing in here. And we're going to cut it into 5 different stages. IF, ID, EX, MEM, write back, and we have this temporary storage space in between the stages. Now, when we actually executing this series of instructions, just watch here. You don't have to copy down. We have a small problem. In this instruction, what do? We're going to end them, these 2 contents, R2 and R3, and we need to write back into where? R7, in the second stage. But in the second stage, right here, this A3, we have a R9. So that's the problem, right? Because in this second stage, we have a R9, so we're going to write 9. However, we're going to write back into 7. So we have to have separate line go back. That's why WA3, W, that must be arrived at the same time as a result, and we're going to write back to in here. In the clock cycle, we're going to write first and then read from this register. Let's do this. First cycle is just a PC plus 4. Cycle number 2, the LDR R1, R3, number 40 on the top of ID stage, and then add R4, R2, number 8 as a IF stage. Since we already have this LDR instruction in the single cycle, now you're familiar with all of this, right? So we're gonna have 3, so I'm gonna use just decimal number this time, 3 for R3, number 44, extended module. Only difference is the 1. We didn't have that before. We had it in here. Within single cycle, we're gonna write back, but it's not anymore. So why we have this? When we're gonna write back in here, that's the 5th stage, after we access to the memory, right? So in order to maintain my RD, I don't want to forget about this RD. We're going to passing this 1 into next stage here when you're getting into execution stage. And then also I'm going to carry that 1 into memory stage. And finally, when I get into write back stage, I'm going to have 1, put it back here and write into the register. Let's move on to the next diagram. The first page is the second diagram. I want you to write cycle 3 there, and now LDR instruction move to the EX stage, and then add instruction is ID stage. Now we fit in another add instruction in IF. So IF R5, R2, R3. Now we have a 2 and 8. My destination register for this add instruction is 4. I had my destination register for LDR 1, so I moved that into 1 right there. And in here, we are given R1 as 4, R2 as a 14, R3 as a 24, and the memory address 48, 4C50 contain these values. Since we had R3, content of R3 is a 24, so that's 24. But in the second stage, ID stage, the reading from RD1 should be content of R2, which is 14. Yeah, right. So when you add these two guys, this is the hex number, this is the decimal number. When you properly add these two, we're going to have 4C. So we're going to move on to cycle number 4. Now LDR is in here, and then add, and subtract. Okay, so let's take a look at the LDR first. In the previous one, in the cycle number 3, we calculate the memory address as a 4C, and then our destination register as a 1. So in this cycle, I want to keep RD as a 1, because I don't want to forget about this guy. And then 4C, the 4C is going to go here, and then read content to 00000AOA. That's right there. So in the next cycle, this value 00000A0A is going to be here, and we want to store that into register 1. That's what we're going to do. And for this add instruction, we need to have a content of R2, which is 000000014, and then the immediate value is 8. When we add these two, it's going to be 1C. This instruction's RD is 4, so we want to keep that. For this instruction's RD is a 5, and then we're going to add R2 and R3. So this is the instruction format for register, register, register. So we have to have a 0 as for this register source, and then 0 for the second one. So we'll have a 2 and 3. And reading content of 2, this guy is 14. Reading content of this is the 24. The next diagram, we're going to move clock cycle 5. We have a LDR in this 5th stage, write back stage. So R1, okay, that's the R1 we're going to fit in here. This is R1. And then content of this R1 is going to be 0x, 0AOA. We're going to put it in here. And for this stage, add R4, R2, number 8. We don't have to go through this memory, right? So this is the bypassing. All the data processing instructions and then branch instruction is going to go bypass. So getting into memory, that's the store and the LDR. Because I don't want to confuse you putting 1 here. So this is 7, right? This is 1. Yeah. Your question is, what if we have R1 somewhere in here? We are updating the content of R1 by placing AOA into here, but we are using R1, or if we have a R1 somewhere here, then we have a problem. That's a really good question. So let's say we have a R1 in here, but we're gonna update R1 in the 5th cycle, but we need to use new value of R1. We are in trouble. That's it, we are in trouble. It's called hazard. We're gonna deal with that probably next time. So we need to identify all of those hazards. And then in order to solve that problem, we're gonna have a hazard detection unit. It's gonna be fun. And then we're gonna forward the data here and there, a whole bunch of more lines add to here. So now all of these control lines, as we move on to next stage, we're gonna carry those numbers in here. When an instruction depends on the result from the instruction that hasn't complete, just like what he asked, right? If we have a R1 somewhere, if we have a R1 in here, we don't have any problem. Why? Because we're gonna write first and then read. Therefore, even if we have a R1, there's no hazard. Make sense? However, in the previous cycle, this guy is R1, then we are trouble, because the R1 we're gonna update, it's gonna be cycle number 5, and this guy is already processing addition here. So that's not good. So that's a data hazard, and there's a control hazard. When we do this execution, and if there's a branch instruction in the middle of this, and we don't know that actual branch happening or not, and we're gonna get the branch also target instruction in the 5th stage and fit it in here. Therefore, we already have 3 instructions in the pipelining. If branch is taken, we're gonna go find that and flush out. Branch is not taken, it's not a problem, it's just go. And the data hazard, something like this. So I'm gonna have R4, R5, and then put it into R1. But in the following instruction, I have to use R1. But when is R1 is updated? In the right backstage. So the time goes from left to the right. Anything you see back arrow from right to left, that's the data hazard. But this guy is not, we said, because we're gonna write first before read. So it's at the same time it's happening. But for these guys, we got data hazard. So identify data hazard is this. So here's the problem. We have R1, and we're gonna update this R1 in the 5th cycle. However, we have R1 we need to use. This R1, we add content of R4, put it in here, and actually it is available right there. That's the result, right? And we need R1 right here. So what we need to do in this case, we're gonna have forward unit from here to here. If we are using R1 as a RM, then from here to here. So we're gonna getting old value of R1 right there. And then 4th cycle, again, we have a problem because that's the old one. But in the 5th cycle, we're gonna update it. So this one is okay because we write first and then read. So we are okay with that one. Handling this data hazard, what we're gonna do, we can insert no ops. Yeah, just put it in the bubble. That's the one action that we can do. And rearrange the code. You can identify this hazard as long as the result is not going to be changed. You can just switch around those some instructions. That way we don't have to worry about this hazard. Or for the data, and then the stall. So we're gonna look into these two. So the first one is a no op. So just holding 2 cycles so that I can forward that into here. But this has cost a lot because holding 2 cycle, just wasting of cycle. So that's not a good solution. So there's a better solution is to forwarding. So whenever we have the result available, forwarding to here. Whenever we have a result available, forwarding to here. So basically forwarding result into here, forwarding result into here. And forwarding result into here, we don't have to because again, that's the at the same time. So book talks about all of these, line values equals we do X, Y, and Z. Here's the forwarding unit. Whenever we have the result is available in this memory stage, we're gonna forward that into this EX stage. So how we do that? Inside of this hazard detection unit, we have this forwarding unit. So compare RD in here versus compare RD within this stage. And if they do match, that means we need to update new value into EX stage. If they don't match, we don't have to take any actions because there's no hazard. So but just by comparing this RD with RN and RM, if it's RD, it doesn't matter. But the source register RN and RM with matching it the RD in the MEM stage, we need to activate this forwarding unit. So we're gonna go through this next time.